in particular us Europeans, but also we have other agencies coming up in the game, as like the Japanese or the Indian, for trying to propose missions to Mars and actually get there in the next years. The most important thing that I want to show in here is not the number of missions, but actually this curve here, these are actually the missions that have failed. So actually going to Mars is really, really difficult. Of course, at the moment now we have better technology than we had in the 60s, but still, as we will discuss later when talking about ExoMars, we see that the technology, even if the technology is ready, there's too many things to take into account, and it is actually very, very tricky. So we can see that less than 50% of the missions that have been launched to Mars have actually been successful. The next lines are flybys, so missions not staying on Mars, but actually just passing by, like Rosetta is one of them, actually somewhere here, this is Rosetta. Then we have orbiter missions, and then landers and rovers. So far, only 7 missions have so far been successful in landing on Mars, and all of them have been American. So this is the main reason also why Europeans and Russians have to work a lot, and this is the main reason for ExoMars to be there, because we have to prove that we can do it. This was for the past. This is how the Mars exploration looks nowadays in the current decade. So we had in the past decade, as I said, a restart on the interest of going to Mars. We have Mars Express here, and I will talk about it at the moment. It's still working nominally. Also, Odyssey and Mars Reconnaissance Orbiter from NASA are still working. The Opportunity rover also still working. Was twin, the twin Spirit exploration rover is no longer operational. Phoenix was also a lander from NASA in the pole at high latitudes. In the next windows, by the way, you probably know, because of the geometry of the orbits of Mars and Earth, there are windows of opportunity, we call them. The launch windows are only every 2 years. So this is what you see here, 2011. This one here happened between Christmas 2013 and 14, then 16, 18, and so on. So if a mission cannot make it within that window, like actually was the case for InSight, was planned to be launched in 2016, but didn't make it on time for the schedule, so it had to be delayed to 2018. So going there, we still have also now MAVEN looking at the atmospheric escape on Mars. We have also Mangalyaan, a new neighbor there with the Indian contribution. MSL Curiosity, of course, that most of you have heard. And then this is, in this window here, this is where we are at the moment with TGO. That's the first part of ExoMars, a contribution between ESA and Russia, and Schiaparelli that we will discuss later. And then for the future, as you see, we have a longer-term plan with a continuation with ExoMars 2020, InSight mission also to look at the subsurface, Mars 2020 from NASA, and then this is, as I said, a part of a longer-term plan. First to look at Mars sample return, and I put here the different colors because as I believe anything that actually goes into the path of human exploration should be a contribution, a collaboration between different agencies. And as we see, as I've shown, it is very, very complex, so we have to push for that collaboration to go together there. Okay, so Mars Express, as I said, was launched in 2003, and it's still working at the moment. I just had 20 minutes ago a teleconference to do the planning for Mars Express in the next months. And this was very important because it was part of the Rosetta family, as I said before, and it was the first European mission to orbit another planet. Okay, I'll move forward. This was the first mission to orbit another planet, and it was the first European attempt to land on another planet. It was more or less at the same time as Huygens, where we successfully landed on the moon, on Titan. But in Mars Express, there was also a lander called Beagle 2, which was part of the, a contribution from the UK agency. It was not really an ESA contribution, it was just part of the UK agency, but didn't work as expected, and I will explain the reason. In 2003, December 2003, Mars Express lander was released and inserted into orbit. I'll explain this a bit because it is also applicable to what happened on ExoMars. So the way this works to deliver a lander, it is that both the spacecraft and the lander are together, flying towards Mars, and a few days before, they're actually separated, and the spacecraft releases the lander with a spin to maintain the attitude, and then the lander is directed in a sort of collision trajectory, or actually going towards Mars, towards the surface, whereas a few, actually typically the day after, the spacecraft is then moved away with a maneuver so that the spacecraft does not reach the surface, but it actually gets a few hundred kilometers away from Mars to get into the orbit insertion. And then the orbit insertion is the first very, very far away. It's what we call the capture orbit. And then we slowly move it down to approach the apocenter of the orbit. So it was at this time, 19th of December 2003, where we used this VMC camera that is now used for public outreach and also science, where we made a picture of Beagle 2, the last picture, the last feedback we got from Beagle 2. The problem is that Beagle 2 did not have a communications. It was supposed to send the data the day after, once it was actually on the ground and open, but we never heard back from it. So this was the last moment, the last information we had from Beagle 2, and that was it for more than 10 years, until actually in 2015, Beagle 2 was actually found. So Beagle 2 was thought, there were many theories and speculations whether it was the parachute or the thermal shield that didn't work, but actually in January 2015, these people from Leicester actually found these bright spots, very, very small. They're actually only 6 kilometers away from the landing site where it was attempted, and as I will show later with ExoMars, the typical landing ellipse are of hundreds of kilometers, so actually 6 kilometers away, this was a success. So everything was great on the trajectory point of view. And actually, even from this little information, these few pixels, we can see that we can recognize, that's why we put here this diagram, to see how these petals, what we call petals that were opening with the solar panels for the Beagle 2 lander to work. So actually, the only reason, the only way to have these petals open was if there was a soft landing. So actually the landing was fine, was correct. Everything was down where it was expected, and it did land softly on the ground and started opening the petals. The problem was that not all the petals are there. We see there were 5 of them, but we only see 3. And the antenna was under the last of the petals. So we could not get any of the signs back. Actually, it's likely that some of the instruments actually did operate, but we could not get any data back. So this is the main lesson learned from Beagle 2, is that you want to have communication at all time. Because even with very little information, as we see here, just with few pictures, we kind of know what happened, but we are missing all the information from the descent. And this is a key point when I will discuss about Schiaparelli. Then in Schiaparelli, we do have all the data from the descent, and we can reconstruct everything that happened. No. I mean, it would cost a lot of money to go and open them, yes.
So you said communications all the time. Okay, you know what happened.
But you know what happened. But the level, okay, not scientifically, but technologically, you know what went wrong and you can fix it for the next time. And this is the main key for Schiaparelli later on. But that we know exactly what happened and we can then fix it. With Beagle 2, we had no idea until January 2015. And still now, we don't know what really happened. We can guess. It was the opening mechanism, but maybe it was not in the exact right geometry, we don't know. In that with Schiaparelli, we know or will know soon. Okay, so Beagle 2, yeah, go ahead. Yeah, look at this, and we go back when you see Schiaparelli. It is very different. The picture is very different. No, no. Of course, this is speculation, huh? But this is seems. That's why I see it. All we can do with Beagle is speculate what happened. With Schiaparelli, we will know for sure. And yeah, remember this picture, and especially these are almost clear that we can actually see the difference. In Schiaparelli, we'll see later. The picture looks very, very different. Okay, so Beagle 2 didn't work, but Mars Express did work perfectly, smoothly, and is still working and performing great, and actually providing all kinds of signs of a comprehensive study of the whole planet from the interior by using the gravity field, actually the movement itself of the spacecraft itself when passing over certain areas. We can get information on the interior of Mars. Then we can also look at the subsurface with the low frequency radar going through the first layers of a few kilometers of the surface. Then the surface that, well, you'll know how much information we can get from the surface on the geology, composition, mineralogy, and so on. And then also at the atmosphere level, dynamics, temperature, climate, clouds, and up to the ionosphere, magnetosphere, and the relationship with the solar wind as well. So Mars Express is looking at all of this at Mars, but on top of that, we also have the Martian moons, Phobos and Deimos, because, as I'll show later, Mars Express is the only spacecraft that can actually look at Phobos close enough to actually get signs out of it. We are looking at Phobos every 5 months. So, to wake up the people that is sleeping, just in case, to put a nice video, you can wake you up. So this is a summary, if that works. Yes. Summary of some of the highlights of Mars Express. And there's probably music. So this is Valles Marineris. These are 3D reconstructions we do with the stereo camera. So this is real data. You can see the valleys, the water carved valleys there, the indication of liquid water. Also some seasonal and dynamic effects in the craters there. The monitoring of the ice, not only the North Pole, but also in the high latitudes and how it evolves with the seasons. We can see the remnant glaciers, also some effects of the geology fractures and faults in the craters as well. The mineralogy that I will discuss later on, and how we can find these hydrated minerals for the atmosphere, the first discovery of auroras on Mars and over the magnetic anomalies. The subsurface radar, where we can get the thickness of the polar caps, and we can actually find out how much water is in there. With this radar, we can also get information on the ionosphere, how the electrons actually reflect. These are the two Martian moons, Phobos and Deimos. And Phobos, we can get a very, very close look. Deimos is much farther away, but for Phobos we can look at it in very, very nice detail. And we also give support to the American missions. In particular, this is Gale Crater. And, okay, this goes very fast, but the next step is then ExoMars. Okay, this was the nice video done just after the 10 years. We are at the 13 years at the moment. So I will go in detail over a few of these highlights. 1 second. Okay, the first highlight I want to mention is the methane. Methane, as you know, it's a hot topic, and I put it first here because it's the direct link with ExoMars, especially ExoMars 2016. So methane, why is it interesting? First of all, and you can ask Sebastian about this, methane should not be there. Methane is not in any of the models, and even if it were there for some eventual reason, some contribution, for example, from comets or something like this, it should not stay there for more than 100 or 30 years, or sorry, 100 or 300 years. It should be destroyed by the photolysis from the UV radiation or by oxidation in the lower layers of the atmosphere. However, in 2004, we discovered it actually with Mars Express, was the first publication, and in that same year, actually 3 different teams, not only Mars Express, but also Krasnopolsky and Muma published from ground observations that they had found methane. And this is actually the first spectrum, so there was a very, very, very tiny band in here. So there was a big fuss in the community because everybody believed this was nonsense, this cannot be, this cannot be explained by any model, this should not be there. And of course there was also big fuss in the media because this has great biology and geological implications. Why? Because in the Earth, the methane that we have here should also be destroyed. It is also destroyed by the UV radiation, but we see methane in there. 80% of it is actually coming from living microbes. Many of them actually living in the stomach of the cow. And so the 80% are actually coming from organic material being decomposed, and the other 20 to 30% is of geological origin of various types, typically hydrothermal processes in the underground, but combined with liquid water. So these are processes well known on Earth, but we are speaking of 3 elements, which are life, geology, or active geology, and liquid water, 3 elements that we do not have on Mars. So any source of methane related to this would be a major discovery on Mars. So again, this was a very hot topic and is still a hot topic. So at the time there were some ideas of how these could be actually in the liquid water underground. There could be some volcanic or hydrothermal processes, eventually biological activity producing methane and other gases, and then some processes how these could be trapped and then released to the atmosphere. With the years then, between 2005 and 2009, the research continued, and actually in 2005, and this year it was also Muma updated their data set, and then produced this very nice map where they claim to have found some potential sources of methane in the atmosphere that also went against the models that should not be so localized. At the same time, with Mars Express, we are still modeling and measuring the methane, and we saw that the methane was, in particular, was not exactly these points where Muma saw it, but it was actually in different latitudes. In this case, was at the northern hemisphere. But more interesting, it was not located in there, like Muma said, not in a specific point, but it was actually moving in the different directions, was circulating through the atmosphere, and in some seasons was actually completely disappearing. And this was then, what was agreed by the community is that more data was needed, and in particular we needed more resolution, because all of these was very, very, very low, the signal was very low within the capabilities of the instruments themselves. So everybody was waiting for the results from MSL, and there was also big fuzz as well. I remember the first planning telecom when we saw this, just when they first published the data in 2013, and they said, no, there's no methane, stop this nonsense. And I remember discussing with some of the Mars Express PIs that said, okay, stop this nonsense of the methane, now it's clear, there's nothing in there, we should stop this. PFS, the main instrument looking at methane on Mars Express, insisted that actually they didn't observe methane at that time either. So they were actually not surprised by this, and they insisted that this could come back. And actually MSL, the year after, actually they came back and said, oh, actually there is a little bit of methane. And the funny thing is that this is actually, I think this was the first measurement they did. And then you see actually how methane, after a few months, this is a whole Mars year, it can vary 10 times more or less. So this is, again, also against some of the theories that if methane is there, so we need to find not only a source where the methane is being produced, but we also need to see how the methane disappears. So either it disappears completely from the atmosphere, as I was discussing with Sebastian, that it might actually be diluted in the atmosphere, so we cannot be or dissolved, basically spread all over the atmosphere, so it's below the the detection level, but then it can then move to the poles or different regions where it can be detected. So all of this is still a question mark, and there's all kinds of still going on models to try to explain how this process can actually come and all the chemistry in the atmosphere to reproduce this. But this is still an open question, and this is the main reason why we have ExoMars 2016, the trace gas orbiter. It actually gives the name to the orbiter itself. It is an orbiter looking for trace gases, in particular methane, but many other gases as well. But methane is the key in here, and that is why we have 6 spectrometers in the infrared and UV to look at this with hundreds, with resolution 100 times better than before. Okay, another hot topic on Mars, also related to Mars Express, but also in general, is liquid water. Liquid water and its link to life. Why do I link it to life here? Is because, we don't have much time to discuss this, but you know the conditions in Mars are extreme, but not as extreme as we could think of for life. If we see at the Earth, if we look anywhere in the Earth, any square centimeter anywhere on the Earth, we will find life. It doesn't matter if it's the driest place or the wettest place in the deep ocean, or if it's the hottest place or the driest. It doesn't matter. We will always find life in there, except maybe for the lava exactly on the volcano, or some lab somewhere. Maybe here at the EAC, we might find some square centimeter. But for the rest, we can find life in any condition on Earth. And actually some conditions, like in Rio Tinto, this is a place actually in Spain, with very acidic water, where life should not exist, but still is able to grow in there. And this is very interesting because it might actually have similar conditions to what could have been in Mars in the past. The only condition that we see on Earth that is actually triggering the existence of life or not is not really temperature or pressure. Even oxygen sometimes we don't need. We can just find energy somewhere else. The one key element that is needed for life is water, liquid water. And that is why, in order to look for life as we know it, at least, we are looking for water. And not only the present, but also the past. Okay, just a point here, because most people think that there's no water on Mars because of the temperature. But actually it's not that much the temperature that matters in the Mars atmosphere. It is actually the pressure. If we see this graph that most of you are physicists, so you know this, but this is pressure and temperature. So at the what atmosphere on the Earth, we would see that actually below 0 degrees, water is solid, it's ice. Then between 0 and 100, it's liquid, and after 100 degrees, it goes into vapor. On Mars, we're just below this, what it's called the triple point. So actually on Mars, we can get temperatures that are actually close to 0 or even above 0 degrees, but this ice would sublimate and become automatically vapor. But as you see, we are just below this triple point. So if we change especially the pressure a little bit, for example in underground, if the ice starts to sublimate, the pressure could increase, and then we could start to have the conditions for liquid water. And also this is for pure water, but we start adding for example salts into the water, this graph might change as well. So this is some of the indications that have been found of potential liquid water. There's a lot of studies, a lot of evidence, not of liquid water directly, but of the traces of water, of liquid water. So this is important. Okay, so talking about liquid water, this also has implications, as I said, about life, because as we know it, what the definition of habitability zone in the solar system, basically we know that the Earth is our reference, is our standard at 1 AU. And then we define the habitability zone as the two extremes that we know, which is basically the two neighbors that we have. On one side we have Venus, which is reasonably close to Earth, so it's not as extremely close to the Sun as I think it's actually only 30%. But just by changing the conditions a little bit, then we turn into this greenhouse oven with the crazy temperatures that Sebastian showed before. And on the other side we have 50% farther away, Mars, which turns into this global fridge. So we have to understand, by studying Mars and Venus, where are these limits? Where are these limits, especially if we're looking for life in exoplanets and all these things? Then we have to understand where this line stands. I'm not talking about Mercury because it's far too close and what I call the frying pan there with almost no atmosphere. So this somewhere here, and we have to understand how this evolution worked. So talking about evolution, okay, just pass this image. So this is Mars as we know it now, but there are a lot of theories, and I will show you just a couple of them of how Mars could have been in the past. So there are some theories of a global ocean that covered the whole of Mars. There's discrepancies whether it covered the whole planet or only some regions. There's other theories of a tiny reservoir of liquid water in the north, and other theories that I will show later also of a bigger ocean covering all the northern hemisphere. And then the question is whether that liquid water then triggered actually the existence of life. There were the conditions, so there was enough pressure for the liquid water to exist, and could the life have existed? And if it did or it didn't, the information of why did it evolve on Earth and not on Mars, or also other theories of panspermia, whether actually the life evolved in Mars and came to Earth. There's a whole set of theories then that are triggered by this. Okay, so to start on the evolution of Mars, just one quick look at how Mars looked today, just in case you know just very rough. I'm not a geologist, and I was hoping to learn something tomorrow in the TADED that someone explains me all these things. But okay, what I can see just as an amateur geologist, I mean, looking at Mars just at the global map, we can see the first the dichotomy, the lower part. This is elevation, by the way. The lower part of Mars, the southern hemisphere, is in general a few kilometers higher than the average, and the northern areas are lower. All the maps of elevation you'll see in Mars, they always use the blue color for this because this has been studied for years. Again, for this theory of the potential ocean in the northern hemisphere, and we can actually see here some features of fluvial features of canals that have been studied, have been demonstrated to have a liquid with the density of water with the same physical properties of water. So it is from just visually we can already see that this really seemed like rivers finishing in this ocean. And actually there's been studies in the 70s with what they call these shorelines all over this dichotomy boundary. There's also many other theories against this because this does not really follow the equipotential and so on. But okay, this is a long story. The idea is that it's obvious from here that we can see the upper part, the northern hemisphere is lower. And by the way, it's just also younger. The lower area here, this higher, you can see already from here, it actually has a lot of craters in there. So the number of craters indicates just visually that it's much older. It can actually get back to 3.5 billion years, whereas the northern hemisphere is much younger, or has been eroded by something, either dust or liquid water. So this is one of the theories. For example, from Mars Express data, if we look at the physical properties of the soil, by using MARSIS, this is this radar that looks at the subsurface. With this radar, we can do analysis of the dielectric constant of the surface, and actually by looking at this dielectric constant, doing some simple assumptions here to explain it. If we look at just pure basalt, it would have a high dielectric constant, whereas sedimental surface would have a lower dielectric constant, and actually water itself would have a dielectric constant of about 3. So by doing a map of the dielectric constant, this is actually the publication of the dielectric constant over the northern area, we can see that it matches very well the elevation, and actually it matches very well these shorelines, the what they call these paleo-ocean shorelines that were already found in the 70s. So this was published as a potential indication or demonstration that this ocean did exist, and it was located in the northern hemisphere. This is one of the theories. Some people like it, some people don't like it. The other one, also to see what happened in this evolution, is if we look again in detail then to these fluvial features, so we can see here, we can recognize them, and we can find, again, I'm not an expert in here, but by looking at the erosion features in there, we can see and distinguish whether some of these are actually made out of a liquid with the density of water. Some of them are like this one, which is actually much slower, much bigger, and actually these are, but just by visual comparison, they are actually glacial features. So they are out of ice, not liquid water, but solid water. And then if we look, again, just doing crater counting, we can see already here that this area has a few craters in here, but this fluvial feature has almost no craters, very, very, very smooth. So just by using this crater counting, we can date all of the features on Mars, and then we can, this is after 10 years of Mars Express data, we can then do a graph of the dates of the features that we see on Mars. So this is today here, and then this is 4.5 billion years. This is looking at the past. So we group all of the publications from the high-resolution camera. We see all of these are actually grouped, all of the volcanic features found on Mars. And we see here that all of them stopped somewhere here less than 1,000 million years ago. So around 500 million years ago, there was something here where we cannot find any more activity of the volcanoes. If we group then all of these fluvial features coming from liquid water, we also see the same. It's the same feature. We find many of these, but all of them stop at a certain point here, around 500 million years. All of them stop. There's nothing younger than 500 million years. On the other hand, if we look at these ones, the glacial features made out of solid water, of ice, then all of them are actually younger than this. They only start in here. So they are much, much younger, these features here. So just by looking at this and counting the dates, we can see that obviously there's something here. Something weird happened here at the planetary scale. So this is not only one area, so this is the whole planet. There was something here where the whole planet activity stopped, and the atmosphere, because this is, as I showed you before, this is driven by the atmosphere itself, the pressure mainly. There's something happened to the atmosphere where the water stopped to be liquid and became ice. So we have to understand where this comes from and the evolution, why this happened. Then I'm going then to the next step is by looking also with Mars Express data, we can also look at the spectroscopy, and we can then analyze spectroscopically with analyze the composition of that surface. And okay, first of all, well, before I get into details, I'll just show something. Basically, we can find hydrated minerals in there. So minerals that have to, the only reason to explain them is that they have been covered by water, not only for a few years, but actually a few thousands and millions of years. But when we look at these minerals, they're not where we were expecting from the other theory. The other theory says that all of these was covered with an ocean. But we find these minerals actually in the lower region. And if we look at this, there is a valley here carved by a potential river that ends in the ocean, and we find minerals everywhere except in here. So from this theory, from these measurements, we actually see that the ocean, the stable ocean, the real stable ocean that covered the whole planet was not on the north, but it was actually the theory then. Okay, well, this here, then we have to then go back into the history, and then actually this theory says that the Northern Ocean was actually a short-lived ocean. The important one mineralogically speaking, was this one here that actually covered the whole planet. So, okay, this is still ongoing work. There's many theories then to actually study the evolution of the planets and how these evolved. And of course, there's no consensus in the community, but it is of course interesting. The one thing that is clear is that there was liquid water, and there was a lot. Whether it covered the whole planet or the north, it's still TBC, but there was a lot of water, and now we don't see it. So where is it? The first idea that is also being analyzed with in particular with Aspera, a plasma instrument on board Mars Express, but also with contributions of MAVEN, of course, from NASA, is to look at the water escape. So did the water escape? And actually, if we look at the ions that are being dragged away by the solar wind, if we look at them, most of these ions are actually hydrogen and oxygen, which then, of course, obvious indication of water. And it's actually losing 1 ton per day. This is, okay, depends, the number changes between Aspera and MAVEN, but in general, we can see that it's actually 1 ton of water being lost by Mars every day. But if we then count back for 3.5 billion years, then this would give us only a 1 meter of global ocean. That this is the number that is used. They basically take the whole of the planet and cover it with water, ignoring the surface feature, to more or less measure how much water was there in the planet. To give you an idea, the Earth has a global equivalent ocean between the oceans and the poles and the water in the water vapor in the atmosphere of 3 kilometers. And with this water escape, we can only explain 1 meter. So either it was just a little, how to say that, a dump, but I mean, this does not explain by itself the amount of water that we see, geologically speaking, and from the mineralogy. Also, this is not enough also for the CO2, for the atmospheric loss. We would need a lot of more CO2 to have the pressure also for... This is what it's been right now, yes.
Would that rate be higher if it was could that rate have been higher based on surface water coverage?
Yeah, I think so. I can check. I was checking the other day also because this has been updated then by MAVEN, and then reconstruction backwards is not easy. How do you do this is not easy. Okay, this is one of the values being put on the table, but this is, let's say, far from being enough. There is another study, by the way, on the HDO, the deuterium actually, and that also gives more indications on that side. But I didn't include it here because it's deuterium, for example, is from NASA, it's from Villanueva, so it's not related to Mars Express. I didn't include it here. What?
Those rates are ion escape rates, right?
Yes.
So it implies photo dissociation of water vapor. Is that what?
Yes, in the ionosphere is dissociated. Yeah.
But could it be another reaction that gives hydrogen and oxygen?
Another reaction for the escape, you mean?
To give that quantity of hydrogen and oxygen, because it's not directly measured, right? The water vapor.
The water vapor, yes, it is measured, but with different instruments. Yes. Sebastian, you want to say something there, or? Okay. We can leave it for the discussion, then I'll finish it. So what I wanted to say here is just that by atmospheric escape doesn't explain the whole quantity of water. So there's a lot of water that is missing. So where could it be? Then the next theory is then that it's actually still there on the planet. That is actually there still on the poles or in the form of ice. And this is why we use MARSIS, the subsurface radar, where we can look at, if you think of this as an ecography that you do to you when you break a bone, actually it gets through there. So these are actually the reflection. The first reflection we see is the top of the surface, but then the signal gets through the surface, and we can see a bright feature in here. Then okay, it's not horizontal because of the dielectric constant in here. This is what we have to correct it. So if we correct by the dielectric constant of the ice, then we get the bottom of the pole. So we can actually then reconstruct in 3D the polar caps and measure the amount of water that is still in there. And we can see already that the ice in there is between 10 and 50 meters, depending on the study. So we have an indication that already it is mostly driven by the ice, and this is only the poles. If we start looking all over the surface, there's many other studies that are showing that this is actually below the surface still. Okay, another thing that we're doing with Mars Express is, of course, the global climate model. This is actually done in the institute there where Sebastian is. And we are taking all of the information from all of the spectrometers to actually get improve our understanding of the atmosphere of Mars. Go a bit faster now. Phobos I mentioned before. This is because of the orbit of the spacecraft itself. This is the orbit in which is proceeding, is doing a hula hop around Mars. So every 5 to 6 months it's actually crossing the orbit of Phobos. So we can then measure it and take images and spectroscopy of the surface of Phobos very, very close. We have here, for example, a very nice image here with Jupiter. Also a conjunction sort of Phobos and Deimos. They're actually a few thousand kilometers away, but they can be looked at together. In this image, you cannot see it here in this light, but you can also see the Galilean moons here of Jupiter. And okay, I will not talk much about Phobos, but just to show that this is interesting because it has implications in the origin of Phobos itself. The historical theories said that these were captured asteroids. But you know a lot about asteroids, much more than me. But if you, from the models, actually it is very difficult that an asteroid is captured by a planet, and moreover is, on top of that, is exactly in an equatorial orbit and almost circular. And moreover, it's 2 of them instead of 1. So it is actually more of an indication of a potential ring, or also coming from an impact, a great impact on Mars. And that is very interesting then, because if we're thinking of a Mars sample return mission, it might actually be much easier to go to Phobos instead of Mars. We can get a sample of Mars, well, not for free, but much cheaper than going to Mars. This is why the Russians were trying to do this a few years ago, and we will keep trying. Okay, so this was the past and present of Mars Express so far, and then I'm talking about the present and future plans with ExoMars. So ExoMars, first of all, is not one single mission. It's a program that combines 2 missions, an orbiter in 2016 and a surface rover in 2020, in collaboration between ESA and Roscosmos. This is the ExoMars 2016 mission, the trace gas orbiter with the 4 instruments, 2 European and 2 Russians, and the Schiaparelli lander that separated on the 16th of October. It was the mission profile. Okay, I'll skip this. Was launched, by the way, with a Proton launcher, Russian launcher. And the technological objectives of the mission was, on one side, the entry, descent, and landing with science instrumentation. And I'll discuss this more about this. And relay communications until 2022 for the future mission of the rover. Actually, in these 2 technology aspects here was to experiment the entry, descent, and landing, and actually we have a lot of data for that. And the relay communications, this was a key. So the big problem for the rover 2020 was not the lander itself. Was without the lander we can still launch the rover. Without the orbiter we could not launch the rover. So we do have what we need for the rover, for the continuation. We do have the telecommunications antenna, and we do have the data from the landing. And then scientifically, that's what we are coordinating at ESAC with the instruments, is the study of the Martian atmosphere, in particular the minor gases and the potential sources of it, combined, of course, with the camera for the surface. Okay, I'll skip this video. This is just the arrival at Mars. Okay, and then I'll go to Schiaparelli. The lander itself, as I said, was to experiment and demonstrate the technology for the entry, descent, and landing. So it's a big process and a lot of elements that we had to test, and we have the data for those. And inside there was the EDM with instrumentation to observe the atmosphere and the conditions of the landing spot. But the main part of it was the descent probe. And the key elements of the descent probe. For example, one of them was the thermal shield that I'll show you also later. But the parachute, for example, we are testing technologies within Europe for these hypersonic parachutes that have to be open at almost 2,000 kilometers an hour. So, of course, this is a critical element, and we have demonstrated that this worked in the same way as the thermal shield. This was the landing ellipse where we were attempting to launch. As you see, this is the scale, is more than 100 kilometers away. And as I showed you in Beagle, we were very, very close to the center. And also in this time, we were actually found exactly in there. This is the sequence itself. The Schiaparelli was entering the atmosphere at this so-called intercept point of 121 kilometers, and we were getting there at 21,000 kilometers an hour. And we had 6 minutes from go to this great speed of 21,000 kilometers down to zero, or actually a maximum of visibility of 10 kilometers an hour. And then we had all these different elements. The first one was the thermal shield that was operating from the 121 kilometers down to, what was it, 11 kilometers. So it was the main critical element. The first one was the thermal shield. Just one fun fact that I learned only a few weeks ago, and I need to share it because it's amazing. Can you guess which material is the thermal shield made of? That's what I thought as well. Not. I can tell you is the main contribution from Portugal to this aerospace industry. It's not cod. It's not fish. No. It's cork. Actually, the main element of the material for the thermal shield is actually cork. No, it's actually real cork from the trees. Of course, there's a lot of this. Of course, it's not just cut from the trees and put in there with scotch. There's a lot of processing in there with the phenolic resins and also polymers of different elements. But at least 50 or 60% of the material here is actual cork. So it's amazing. So and so with this cork, and actually it did work. So if you want to make it work, make it simple. It did actually reduce from 21,000 kilometers down to about 2,000 kilometers an hour. When the parachute was deployed, everything went smoothly, perfect. The parachute was working perfectly, and then at about 7 kilometers altitude, then the front shield was released. And then this was the area where with the parachute working, and it was working smoothly, this was from 7 kilometers down to 1 kilometer. So the Schiaparelli lander should have been released from the rear shield and the parachute at 1 kilometer altitude, and then use the thrusters to slow down from the last 250 kilometers down to 10 kilometers. It is just the last kilometer. What I can tell you now, well, actually, I'll show it here with a video because this is worth sharing. Okay, sorry, I cannot get rid of that left part anyway. So this is the cork doing its job, then burned and turned into actual carbon in the end, that is sublimates. Then this is the parachute release, you'll see now. This also worked perfectly. 1,700 kilometers an hour. And then going down to also the front shield. Up to here, everything is timed. Okay, so everything is timed, and at this point, at 7 kilometer altitude, this is when the actual radars, these are the radar antennas, altimeters, that are actually measuring, and the lander itself started collecting information and processing it, and taking autonomous decisions. And this is where actually things started to get wrong. This altitude should have been 1 kilometer, but actually, and then this should have been thrusting for 30 or 40 seconds. To give you an idea, this is burning 1 kilogram of fuel per second. So this would have to go down for 30 seconds to slow down. The problem is that the parachute was released much higher, at 3 kilometers altitude instead of 1 kilometer. And only after 3 seconds of thrusting of the rockets, the onboard computer thought it was landed already. At a certain point, you see in the telemetry, actually, it says, okay, touchdown, I'm on the ground. I'm starting to start operating the instruments and actually start taking measurements with the thrusters off while it was at an altitude of likely, more than 2,000 meters. And this still under analysis. The report, by the way, is actually coming next Monday, and will be public, and we can all read it. But this is more or less what is known now. But actually, all of the elements. The good thing is that all of the elements did actually work. Hardware elements. So it was just the onboard processor that processed the information incorrectly and took the bad decision. So it was when you said, for example, for Rosetta in the future to make it more autonomous, you might want to think about it. You have to be very sure that the autonomous decisions are done in the right way, because it is tricky. The good thing is that a software bug is very easy to fix. If we had found any problem with the material, with the cork that I mentioned before, with the material or the hardware of the release mechanism of the parachute, or the thrusters themselves, the thrusters did work as they were expected to work, only for 3 seconds though, because they were commanded to be stopped. So this was the reason. So the signal was lost. Indeed, we didn't know more about it until a few days later with the MRO low-resolution camera, was actually taking a picture of the area. And here, this is a GIF. So only a few days later, we could find already this black spot. And already here, this is, I think it's 20 meter per pixel, something like this. You can already see that this is very different to Beagle 2. So it's not a white spot, but a black one. You can already see here this black spot here and a white spot down here. So this is actually the parachute. A few days later, we got the high-resolution image from the high-resolution camera from HiRISE, and we can see actually the features, the black feature here, the white one down here. So the white one, we can see both the parachute and the rear heat shield. This is the front heat shield, a few hundred meters, actually about a bit more than a kilometer away. And we can see this dark spot here. Again, it's very different from Beagle 2. Then also a few days later, we got the color image. And we can see here, well, actually it looks a bit better on my screen, but anyway, you can see here that there is actually a crater with actual ejecta around. And actually these are very likely to be pieces of the lander. There's one of the theories, okay, now speculating, that these might actually have exploded on the impact on the ground, because it was actually full of fuel. But okay, this is pure speculation. We will see next week what happens. No, I have no idea, and that is it. I'm very curious to find out. That's one of the speculations. We can share all kind of speculations over a beer later on. This is another fun fact. Looking at the parachute, this was the image taken on the 25th of October. The front shield, the back shield, sorry, and the parachute. And this is just 6 days later. The shape is completely different. And this is probably very likely to be the wind that actually has moved the parachute itself. I cannot tell. I just extracted from the I extracted it from the web page. I know what you know in this case. Okay, finish my last 5 minutes with TGO. TGO is working perfectly. The orbit insertion did work exactly as it should. It was burning for 2 hours and 20 minutes at the arrival. It was burning 1.3 tons of fuel. The spacecraft itself is about 3 tons. It was almost 4.5 or 5 tons with the fuel itself. And then we got into this capture orbit very far away, just enough to not fly away from Mars. So we get into this very high elliptical orbit, 500 kilometers at the pericenter. I think it's actually down to 250 at the moment, and 100,000 kilometers at the end. The nominal science mission, we have to be at 400 kilometers circular orbit. to have enough fuel to do that, well, I don't know, but it's probably many, many tons of fuel to actually bring the apocenter down to 400 kilometers and make it circular for science. The only way to do that is actually break here the spacecraft by using the atmosphere itself. So we are going down in the atmosphere, lower than 200 kilometers, to actually use the solar panels and the whole spacecraft itself to slow down the spacecraft for every pericentered passage. But this is a very, very, very slow process. Every pericentered passage we are slowing down a few, probably less than a centimeter per second, and this is why we will be spending the whole of 2017, starting in February or March, ending at the end of the year, to actually bring down. I don't know, and probably maybe they don't even know, because this is actually after every passage they have to see where the spacecraft is and then correct it eventually for the next passage. So this is a very time-consuming effort, not only physically by the spacecraft but also by flight dynamics. Yeah, well, and that's another point, of course. Then you don't know. I mean, you know by the models how much density in the atmosphere, but this might vary, and you need to check, because if it slows down too much, then you can actually reach the spacecraft in the next pass. So you have to be very careful. Okay, again back to the instrumentation. Okay, I'll just go to the next one. These are the 4 instruments here: 2 Europeans, 2 Russians. The first block is the atmospheric spectroscopy analysis for the trace gases. And I go back to the first graph where I showed you before. The detection of methane was this very tiny band in here with very, very low signal to noise ratio. Actually, in this, I think it was measuring a few million spectra to actually get this. This is what the first spectra from Mars will look like from TGO. So we are actually improving. Okay, I think it's around 100 times better in spectral resolution, and what is more important is about 1,000 times better in sensitivity, thanks to also the new technique we're going to use, solar occultations to do this. So the PFS was just mostly looking nadir, but with TGO, with the spectrometers, we'll be looking at sun occultations, and the absorption band will be much more evident. So we hope, actually, next 21st of November, we are having the first only calibrations of the instruments. So we are only looking at nadir at that moment, a few limps, but no solar occultation at the moment. So we do not plan to have any major discovery in the next month. We have to wait until 2018. But I'm always optimistic, and maybe we can get a surprise in 2 weeks' time, whether there might be something funny in the atmosphere or unexpected. Okay, the next one is the high-resolution stereo camera. Okay, I don't want to mention too much here. The only thing is that to have a stereo camera, you need 2 angles, the point of view, and the way this camera is working, it has this rotation mechanism here that actually passes over a certain spot, and then once after it's over it, it turns and looks back to the same spot. So this is the mechanism that is being used by the camera, and it is, by the way, also color, and at the color level, the image you saw before from high-rise, I think it's about 5 meters per pixel. With CASIS, we will have even better, or at the same order of magnitude for the color imaging. Actually, they like to say this is the best color camera in Mars at the moment. We'll see also in 2 weeks when we get the first image. Another one to mention here is the neutron detector. Okay, just to say, this is a complex process that I barely understand, but basically with the cosmic rays, the galactic cosmic rays impacting the subsurface, actually there's these reactions that produce neutrons, so you will actually be getting neutrons from the subsurface, the first 1 or 2 meters of the surface, but these neutrons would react very easily with hydrogen. So by measuring the quantity of neutrons that you're getting from the subsurface, you can actually induce the quantity of hydrogen in the first meters, which from there you can then induce the amount of water in the subsurface. This is something that was done already years ago with Odyssey, but only with very low resolution, 300 kilometers per pixel. We are going down now to 40 kilometers per pixel, so we can improve the resolution of the past. And these links, by the way, with the subsurface ice that I was mentioning before, we need to find out actually the actual quantity of water that there is still in Mars, not only the poles but spread all over the planet, and this will give us information in that area. Then to the rover, I think it's just a few minutes behind, but just tell you that this is the next step. I'll go a bit fast here. The rover, or the ExoMars 2020 mission, now it actually has been updated. The name, it's called now the Rover and Surface Platform mission, because it has two elements: the rover itself with the main objective to look for signs of present or past life on Mars, and the research for water in the subsurface and environment. So it is, we're looking for life or the habitability conditions, present or past. Technologically, not only landing on Mars but also moving on the surface, accessing the subsurface, and then taking acquiring samples from the surface and the subsurface. And then on the other side, there's this surface platform which will help us then for the descent of the rover, and characterize the surface environment before the rover actually starts moving. The nominal launch was in 2018, but it has been delayed to the next window in 2020 for schedule reasons. And then, okay, let's skip this and I'll show it in the last video. There's the carrier, which is European. Then the surface platform that is, well, this is to show you how difficult it is. This is the Russian launcher that carries a European carrier, that carries a Russian surface descent platform, that carries a European rover inside. So you can imagine how complicated it is to coordinate all these activities. The rover itself has a drill that will go down to 2-meter depth. The American missions so far have only looked at the first few centimeters of the surface, and actually these centimeters there's obviously no signs of life, because the ultraviolet radiation would kill everything that is within the first centimeters. If we go deep enough, we can actually get something that is some organic molecules, more complex, more that are not than that are, let's say, how do you call them? Well, they have not been photolyzed by the UV radiation. Okay, I'll just skip these. These are some of the plans for moving through the landing site. The landing site, by the way, this was the pre-selection. There were, all of them are actually in this transition period between the south and the north. And okay, this is just the summary, so I'll finish just with the video. Well, I get the questions. 5 minutes too much, but reasonable, I hope. Romantic music for the moment. It will get a bit. So this was the launch of ExoMars 2016 in March. This was the original design. In the end, it is actually black MLI. This was the arrival, and the separation we'll see now. It is on the 16th of October. This, as you see here, this is the release. The lander itself is released with a spin to maintain its altitude on the way to Mars. And then, okay, it doesn't show any more details. This is an old video. This was 2018, now it is 2020. For the next mission, also launched with a Proton. And as we see, the Russian launcher that carries this so-called carrier module with the solar panels and communications just enough to for the cruise phase to get to Mars. This is now mid-2021. I think it's May 2021 at the moment. 72 years. It's not exactly 2 years. It's 2 years and a few months, I think. This is much heavier than the lander that we have now. Actually, it has 2 parachutes. Then this is the surface platform from the Russians. This might actually have changed in the past. This video is a bit old and has been updated, and I'm to tell the truth, I have not been involved in the last developments of the Russian surface platform. I know that this surface platform now carries instruments as well. Actually, some of them are even Spanish, actually, done in Madrid. And this is the little baby here, the rover. With the little face, and I always say this, they don't make 2 cameras to make it more human-like, that we like it more is just for the stereo image to be able to reconstruct the distances. This is where the music gets exciting. We are proud of being Europeans. Huh? Okay, this big thing here, this is the driller. This is done by Galileo Avionica, as far as I know. Well, now the company has changed the name, but still, actually I've seen the models already. Is about this big. And this is actually taking the samples, as I said. It has different layers, so it's actually going down and taking samples at different depths. And the samples are then put into the Pasteur module inside. Actually, will be the highest technology at the moment, focused mainly on astrobiology, to then make all the, well, not all of them, but all you can do, all the type of analysis that you would do on the Earth with the gas chromatograph and mass spectrometers in there to understand the possible signals of life, or at least the signals of habitability conditions in the present and the past. Just a message there. At that time, TGO was still flying around, doing science and supporting the mission. And I think that's it. Thank you.